think it's not quite clear, but we can just fill implicit game here. So they say some numerical difference solvers, and so there will be some difficulties with them. And regarding some noises, so we can just implicitly fill the gap. And okay, the abstract is really just concise summary of the whole paper, and I feel like quite difficulty when I first read this abstract because there are lots of words that I could not understand. Yes, for example.
Please think about it. So, does it make sense to everyone? Anyway, they are trying to estimate the parameters of the ODE, but they don't need a numerical differential equation solver. What do you think? Can you imagine? How many people in this room have you fitting the model? That's why it's parameter. Hands up. Without numerical solver. Yes. I don't like imagine how to do it. Can they really do it?
Oh yeah.
Okay. Let's see. That's already very surprising. They are trying to fitting
Kind of people.
to the data, but without serving the
ODEs.
ODE. Hyungjun, what do you think? It's possible or not?
My thought it is impossible.
Yes. So anyway, 2 weeks ago when I went to SIAM conference, this was one of the interesting topic to me. But unfortunately, the speaker didn't explain the detail. So let's see. Okay.
So is there any opinions on the abstract? Then I'll return. Okay. Let's first considering just we have some underlying dynamics and which is unknown. And we only have the observation. By the observation, we will get some data, and this is the data point. And our goal is to connect the data and the unknown underlying dynamics. So to doing that, we often use any kind of model, and we really often use some ODEs. For example, here there is just Rotka which is preferential model. But to use that model, as you see, we need some parameters, alpha, beta, gamma, delta. So our goal is to estimate these unknown parameters to use our model. So this is what we call the problem of parameter estimation. Okay, suppose we have some data, and we can just represent it as this matrix. And we want to know from this data, we want to know the parameters. The often used method is what we call for method. And this is here, just simplified algorithm. Okay, first, just give initial guess to the parameters. And then we will solve all these. And we will get these trajectories. And then we will sample the point. And we will sample and then compare the data and our simulated sample. It will give you some kind of loss. And based on this, we will use some other bank method to give another guess on the parameter. And we will repeat this process until we have some convergent parameter set. So this is what we call for method. And this is, I think most of you may think it is what we usually do with the ODE parameter estimation problem.
Yeah, we do every day.
Yeah, we do every day. So, but let's think about some issues regarding this problem. Okay, first, as you see, we have to repeatedly solve these ODEs, and which is obviously expensive in computational cost. And there's one more issue about it. The ODE solving is really dependent on how you solve the ODE numerically. And there is one just simple but interesting example. Okay, this equation looks quite easy to solve because it looks just. But it turns out that the blue line is the exact solution, and this orange line is just one kind of numerical method, and the green line is another numerical method. So you can see that the explicit ODE method really fails for the ODE. So we always have to care about which numerical method to use when we solve ODEs. So anyway, from these examples, we think, is there any ODE parameters to measure without solving ODEs? So this is really the idea why the WENDy arise.
So far, Kangmin's description for the gap is more attractive than original abstract.
Okay, now let's try introduction to WENDy. So let's consider this simple ODE, which was I presented before, and let's rearrange in matrix format. So let's see. Okay, the left part is just time derivative of our variables, and the middle part is the functions which are written in the ODEs related to that variable. And the last part is our parameter. So basically we want to estimate this part. These two parts are known.
Should we distinguish negative xy?
I don't think so. It's just for convenience.
Okay.
Then, okay, we would like to generalize it in matrix form. We would like using these notations in which left part the U will be the solution vectors, and we have d-dimensional vector. And the zeta, it will contain the functions. Each function, x, y, x, y, these are put it into this vector. Okay, so zeta will be function. And we will write parameter as the W matrix. So this notation will be repeatedly appear on this journal. Okay. So then, this is the start of the WENDy. We will multiply both sides of this expression by some so-called test function phi. And okay, this is just multiply. And we will do integration by terms, and which we will do this expression. And then we pose some conditions for phi. First, phi should be 0 outside the interval 0 to time t, the time interval which we are interested in. And then it should be differential function, and the other positive infinite differential function. So by this condition, we can claim that if phi 0 and phi t becomes 0.
Yes.
So this interpretation is even simplified to this simple expression. Any questions? And okay, this is what we will call weak form of the ODE.
So have you heard about it in your undergraduate class, weak form?
Not really. I think we all will know well about it.
And
In
it's
the PD class.
Yeah.
real analysis.
Yeah.
You know that, so you learn this
Maybe-
weak form, right?
There's some concept called distribution.
Distribution, yes. It's actually a known, very well known concept in the math. But real analysis or functional analysis, they adopted it here. Smart. So let's about 30 seconds. Let's look at the red boxes. And please think about anyway. Left top is the original differential equation, right? It's equivalent to the now. It's not perfectly equivalent, but anyway, it changed to the bottom part. Thinking about enjoy that equation relationship. Anyway, derivative for u is disappears. That's the power of integral by parts. Okay. Happy? Okay, please memorize this red box well.
Okay. Now let's continue. So we have okay. We know that this weak form is anyway defined in the continuous time because we continuously integrate from terms of t. So, but our data is sampled in discrete in time. It is a uniformly sampled, just like this. They are just points. So we need to redefine the vectors to accommodate this discreteness, and it is just matter of numerical things. So let's think of this time lattice, and on that we will scatter the data points, and we will record it as vector, our data matrix. So and that direction is the different variables, and on this direction is evolution of time from t0 to tn. Right? And then we should evaluate functions on each time point. So our previously function vector will be function matrix evaluated on each time. So these are different functions, and they are all evaluated on each time point. And we need to describe the test function. So it is just the same as before, and we will construct the discretized vector. So our continuous form just can be easily discretized into this matrix notation, and which is nothing more than just the trapezoidal rule when we use numerical integration with computer. Okay, this is just how we will practically calculate this expression.
How we can do it.
Okay, then if you're okay, I will continue. Now we have this data and we have the discretized model. And finally, we want to estimate the parameter vector, W. And for that, we will use this discretized weak form. And you may think the most intuitive estimator, what could be the most intuitive estimator of this W? It would be something that minimizes that expression. Because we want these two things to be the same. So we want to minimize that. So, and then we will simplify some notations and define G and B and write minimizing G W minus B. And this would be very familiar with you guys because it is nothing more than just linear minimization problem. So we know the solution. Just some metric thing. So I will give you some interim summary. So in the forward method, we have to repeat solving ODEs. However, with this weak form method, we just only need to solve the matrix computation. And this is just ordinary squares problem. So we can think it is much faster. But unfortunately, this is the end of this paper.
Sure.
So we received some problems, some issues regarding these solutions.
Can you go back? So G and D is next. Here, for instance, G is, now we know the data U, that's just data, right?
Yeah, just
We can do it.
function evaluating
about-
the data.
Pi, pi is test function.
Yes,
A test function can be many, right?
yes.
There are so many test functions. How do we know the G?
So we have to choose phi, and there,
Some pi.
some phi, and also provide some guidelines on choosing phi. But basically, you can use any phi.
Because
Yes.
this equation should hold for any pi.
Any phi.
So that's why we just pick up the,
Mhm.
I see, but we don't want to choose the zero. That's trivial. I see, we may want to select a little bit, not too complex, but still some,
Actually, they just
increasing and decreasing. Okay.
this shape function.
But I think they can try various pi together. Because this
Yeah.
equation should hold for
Yeah,
the
yeah, yeah.
various pi, this one, maybe this, some cyclic one. Then maybe they can improve the accuracy.
But
It doesn't work.
according to the paper, I think they think this
Is it enough?
is the best choice, optimal choice for them.
The optimal choice. Because I thought that we have to choose as many as possible that it becomes better and better. Because this equation should hold for any test function.
Yes, yes. So one possibility, one way is just use this function and translate this function. So use just multiple translative test function to check this condition.
So they first fix the time interval from 0 to t, and then they kind of narrow test function on
Or
it, and then translate it to several different distributions.
and that is on the appendix, but shortly they make several test function, and they can put it on this matrix from time 0 to t, and they will do singular value decomposition to also analyze these functions. I think, but it is just one option to choose test function.
그렇지. 그래서 하나에 대해서 내는 게 아니고 무조건 사실 다 홀딩해야 되는 거야.
네.
옳은 파라미터. 그러면 그냥 여러 개로 하는 게 더 안전적인 거 아니야?
여러 개를 쓰긴 쓰는데요. 근데 함수 형태를 바꾸진 않습니다. 같은 함수
이거를 이렇게 윈도우.
네, 윈도우처럼 이 정도는 아니고.
근데 뭐 나쁘지 않은데 컨셉. 근데
근본적으로 저 디스크리타이즈드 폼
자체가 틀렸을 수도 있지.
그러니까 인테그레이션을 지금 그러니까 사다리꼴 형태로 그거 넓이 근사한 거를 기본으로 하고 있는데 그 얘기는 뭐냐면 타임 그러니까 옵션보드 타임 기반으로 이걸 디스크리타이즈 하는 거거든요.
Can you tell me where that describes with form is given? Maybe we had integral. Yeah. And then how we move to left to the right.
Oh. So this is nothing more than just multiplying this time point in each time and multiply by this length. So it will, like when we do Riemann integral,
So I think we are just looking at a very small time.
Very
Yeah,
small.
yeah.
And then, so in the right hand side, we still have time parameter t, discretized time parameter t I or something.
Yeah, but
But-
that is determined by sampling interval of data.
Yeah, so because we have a relatively small time interval length for the right hand side discretized equation,
Mhm.
the form in the integral and the discretized version must be the same.
Mm.
And when we consider a very naive Riemannian integral like this, then we just take the summation of all the rectangles.
Yeah, yeah.
So this is just one small piece of rectangle, and this is the
But actually we need a sigma, is it?
저
아.
벡터 썸 아닐까?
네, 이게 다
이게-
매트릭스
이너 프로덕트처럼 되는 것 같아요.
sigma예요, 그러면?
네, 다 더해지는
얘가
그
매트릭스로
작은-
정의해놔가지고
작은 렉탱귤들을 다 로우 벡터 형태로 막 만들어서 더하면 이제
아,
이게 리만 썸처럼 되는데 그거 대신에
썸.
트래폴드리달로 바꾸는 건 사실 그냥 한 번 그냥 조금만 더 에러 막 메꿔주는 거니까.
그렇죠.
오케이.
So I think the very crucial point here is we have to capture it with the discretized resolution of the data points. We have to capture all the zeroth order and the first order fluctuation of the test function. So, for example, if we have like very steep test function like this, almost like a step function with infinitely many differentiable smoothing at the end. But if we miss these two quick surge and drop by the data discretization, then we would miss every information from the left hand side. So that's why they are translated in the test function
Yeah,
distribution.
yeah, I think that's why we need to choose the pi very carefully.
Yeah, as long as like we have we are in the ideal case, any function phi must satisfy exact equality, but that is not the case.
그래서 저희 너무 좁아버리면 사실 그 간격이 촘촘하게 안 돼 있으면 이게 문제가 될 것 같거든요. 그러니까 계산에 의미가 없을 수
어느 정도 그 샘플이 저 웬디 나오긴 하는데 샘플이 좀 많아야 좀 그 기존 메소드랑
네. 그러니까 저 테스트 펑션의 서포트 안에 충분한 점의 개수가
맞아.
있어야 될 것 같거든요.
테스트 펑션 안에도 있어야 되고 테스트 펑션의 데리버티브에
맞아요.
서포트 안에도 충분히 있어요.
맞아요, 있어요.
그두 개.
그래서 적절한 걸 몰라야 된다. 오케이. Let's go.
이렇게
그래도 좋은데.
Okay, so okay, we have this solution. This is just ordinary square solution, but there is some issues with the solution, and we will see that there are some kind of dependent residual problem. I will call. So let's just go back to just ordinary square problem. So when we consider this ordinary square problem, we will find the best fit. So equal with the best fit, and you will find the residuals. And in that ONS model, we always assume that each errors, epsilon i's are independent. That is the really only basis of that model. So we will assume they are from the same normal distribution and IID condition. And how about if you think they have some correlation? You know that they are some correlating. Will you and you with the same data, will you give the same fit as the independent errors, or will you give another fit? Okay, maybe you can give this new fit because in this situation, the residuals are more correlate with this new fitting line. So, so when we know that errors are correlated, the situations are become more complex. So it turns out that weak form method also suffers from the dependent residual problem. Okay, demonstrate that with a really simple example. Okay, let's consider more simplified equation. And again, we will rearrange the matrix, and we want to minimize the GW minus B. And for simplicity, let's assume that we have 2 time points. And we will just like ODE matrices and B. So this is not really important. And we will just want to calculate the residuals. And with this expression, we will have this just some kind of complicated expression. And let's look at this expression. Okay, we have 2 residuals. And in fact, that X0 and XT, they are all from observation. So we usually say that this observation is composed of real data and some observation noise. This is our usual assumption.
We assume that they are independent, right?
Yeah.
At this point, okay.
So at this point, you can just write down some independent noises.
More noise, okay.
Yeah, and there are from some distribution, but at least they are IID. But if you put this noise expression into this, it's just erase some unnecessary constant. But at least you can see that we have some correlation among the residuals. So in our problem, residuals are no longer independent. So you can say that we are not really good with ordinary scales. But luckily, there is already some method regarding this, and which people call generalized scales. And so it deals with situation where residuals dependent or heteroscedastic. And okay, we will do the application of covariance matrix of residuals, the omega. And in this situation, and within our situation, the omega, the covariance matrix has non-zero off-diagonal components. So different residuals are correlated, can be correlated. Okay. So in ODE problem, we minimize the GW minus B, and it was our solution. But when it comes to generalized discrete problem, we will minimize very similar, but it's divided by the omega inverse term. And I will not really deeply describe about it, but it can be interpreted that they will penalize the large variances because it is omega inverse. But luckily, it has quite good solution because they are so similar.
What is omega? Sorry?
The residual covariance matrix.
Okay.
So when the covariance matrix are just identity matrix, it comes back to ODE problem. And that is when independent and almost specificity is satisfied. Okay. However, we don't know the expression of omega. And I will just treat this part very quickly because it is too technical and I don't understand fully. So they approximate the omega matrix with some complex expression. And there is an algorithm to start from ODE solution to GLS solution. Let's start the initial guess as ODE solution. and then compute the approximate
covariance.
covariance. This
So we can calculate
approximation.
the residual.
Yeah. So we can update this omega W matrix, and we will repeat this process. And by this iterative process, theoretically it can be converted to GLS solution.
So think about it, everyone. So here, omega is a covariance matrix. For this, we need to calculate the residual. To make the residual, we need a prediction. Because to calculate the error, you have to make a prediction first. So what they did is, they predict the omega hat first. Because now we know the omega hat, we can calculate the error, right? Based on that error, we calculate the omega. And then by plugging this omega, we calculate the solution again. Then now we can calculate the residual again. And then we repeat it.
Yeah.
It's a pretty cool idea. It seems, typically it looks like it should work.
Actually, there is made for this algorithm. It's iteratively related with Pierce algorithm. And I think it is quite popular in, especially in finance or in the field, because they are always front with very severe noises.
So I think this is this IRLS seems useful algorithm for anyone here, because in the fitting we never consider the residual distribution. Okay. So what I know is if you give a talk when statistician exists, if you just do the least square, they will criticize. Because unless there is IID assumption in the residual, we cannot do it. But there is a way to overcome it. That's very good. Nice.
So, in summary, what is WENDy? So WENDy is first deadly from estimation plus this IRLS method.
Nice.
It is they are the main of the WENDy algorithm. So now let's see some results in the WENDy. First, they compare the ODE solution and their WENDy, ODE combined with IRLS algorithm. And they simulated Lotka Volterra with some noises. And they estimated the error of parameter estimation. And you can see that from this plot. Compared to ODE solution, the WENDy is much more improved, about 50%.
Oh. What is that graph? Y-axis and x-axis.
So this is just, they use more time points, 64 time point, 128, and 1000 time points. And in the color, there are different noises. And this is decrease of error compared to ODE solution and WENDy solution. So after doing the iterative related method, the parameter estimation error really decreased significantly. So it tells us that really that non-independent residual gives us problem. And okay, this is the final part of this slide. They compare first WENDy and just forward method we introduced at the previous. And they also made some hybrid method, which is take WENDy solution as initial guess for forward method. And okay, in this direction, they simulated with more noise And first row were shorter data points and more data points. And these axes are time, computer time, and these axes are error. And okay, for example, here we can. Oh,
No, not here.
okay, this is the original forward method, and this is the WENDy method, and it really decreased the parameter estimation error and the computation time 10-fold. Because it is really intuitive, because we don't no longer need to solve the ODEs. We only need to iteratively doing matrix calculation. So it is much faster.
So here, triangle is the mean of the E2.
Yeah, I think median.
So, did they mention about the time difference between the observations? The interval between
That's
them?
what is.
So, the more data means that shorter time interval.
No, I don't think so. More data is just longer time series,
Longer
but
time
with
series.
same time interval.
Okay. Then makes sense.
So
근데 furthermore, I like this plot. X-axis is computation time, y-axis is error. Usually we draw the separate zeros. Okay. And it works well for this example.
yeah. And they try some other examples, and they were also very
Good, very good.
Oh, but in
Yeah.
the last figure,
in the last year. Honestly, they didn't mention about why this happened.
it seems like because the noise is higher, and like indeed has higher error.
But I think it is only for this example,
This example.
and for other
So when they add this 5%, 10%, 20% of those noise are
just additive mode.
additive noise to
Observation.
Observation data.
individual data points.
Yeah.
Yeah, then it might be because, so if there is no noise, no observation additive noise, like 5% or something, then the dependence structure from the model, from the dynamical model itself becomes important. And WENDy is trying to capture those dependence. That's why they perform better in the left column. But in the right column, if you have large additive noise, then from the model itself we have dependence of noise, but we have large independent noise. So now we have the noise are dominated by these independent noises, and WENDy still supposed to work better, but the problem is in the forward method we don't use any any weak form. So in the forward method when we perform the forward simulation we have very nice numerical sort. So as long as data observation noise are completely independent, then the forward method is supposed to be better than WENDy. So I think the right column is still natural result.
Good.
Okay, any other comments?
Good.
Okay.
Are you done?
Oh, you can ask.
So did they use the forward method you mentioned? I mean, guess, sort,
Yeah.
guess again.
Yeah.
I think this might be too bad because you can initially construct a loss function using the parameter and optimize it. I mean, in the forward method.
But too bad.
I mean, what they used seems to be a bit bad. I wondered why.
But when we construct the loss function from parameters, from the parameter to the loss function, we have to perform the word simulation. There is no like closed form relationship between parameter and loss function.
No, you only need to discretize the velocity. Discretize velocity and use the observed time data.
But my concern is knowing the ODE solutions velocity is not might not be that easy. How do we know it? Y derivative equal to some equation, but in the equation we don't know the product.
So yeah, parameters are the one to be optimized.
Right?
So, but in the, so I got the point, but in the fourth method they mentioned, I think they just perform so to compare the observed velocity vector and observed data points, then we need to use only the data resolution we are given.
Yes.
But in the fourth method, I think for a fixed parameter set, they just perform the fourth simulation with a nicer, like, discretized finer data points, and then compare the simulated trajectory and the given data points, and then keep doing that to get better estimation.
And
So
then,
that's why they are more slower.
and then test function is another thing is test function we know what it is exactly. So that we can calculate the derivative with everything perfectly.
Okay. So I will give you just quick summary of this chart. So they were trying to make some parameter estimate method without solving ODE, and they provide the weak form to do this. And for concerning the residual issues, they applied IRLS, iterative relativity skew method, and WENDy is faster and more accurate, they claim. So this is end of my presentation. If you have any question, please feel free to ask.
Right? Any questions? No,
Just for a quick question, so in your description, you set the delta t as constant, so
Yeah.
is it essential or not essential?
I think it's just numerical issues,
No.
not essential. You can think about rather than trapezoid the rule, other rules to discretize the equations.
Any other question? Yeah.
I have a question. In the performance of comparison figure, here, what is the meaning of each data point?
I think they are all different realization of the
They use
simulation.
different model?
No, they simulated with different noises.
Different noise,
Yeah,
but the noise levels are same.
the noise levels are same.
But they use the same model.
Yeah, yes, single model.
So I think individual data points have different random seed.
Yes.
But the variation is.
Quite large.
Yeah. So
Yeah, that's true.
Wait, is it look?
Yeah.
1%, 0.1%, this is 10%.
yeah, but for the comparison, with the comparison,
Or
you can see
maybe data points are different, different error. It could be
Different error.
kind of 1024 data points are repeatedly.
Oh yeah, it's regenerated.
I think yeah.
So they have like true solid
True
line.
solid line and then give a one random shot, second random shot.
But I can see the lot of overlap between the different method.
Tommy, can you go to that weak form? Can you?
Here,
Yes. Okay. But anyway, the idea is from here here, original u derivative disappear. There's no more u derivative here. Because u is unknown. Unknown's derivative is u is observable, right? U is given data set. But u's derivative, if we have very small interval, then maybe you can estimate the u derivative. That's happy, but typically we have it's sometime between these two time points, maybe we have this kind of U shape, right? So knowing the u derivative is impossible, typically. But now here, no u derivative. The derivative moved to the pi. And pi, we can use some whatever you know, a function. So derivative is now moved to that node function. I think that's the key idea here. By doing the because in the high school we love the integral by parts. What is the integral by parts? Moving the dot to the another function. But that's a typical technique in the many math, right? But they use it for the parameter estimation. I think that's why this is a cool idea. Think about it. Where can we use it? For your own project. So
Can we improve Gobi with the
So think about it, really. Can we get the Gobi idea from this form? That's another. Because Gobi is based on the y derivative, right? Actually, we know it that that derivative is sometimes not good.
Big error.
Big error, indeed. Because to use the Gobi, we have to compare the sign of x difference and y derivative differences. But when the discrete, how we do is, for discrete time point, we interpolate it, and then we estimate the derivative at each point. We didn't like it. So, can we guess that kind of idea from this weak form? I think that would be really cool.
We go big.
Oh, we go big. Wow. Beautiful. Let's call weak Gobi. Weak Gobi. The name is made. We just need a method older than Hungry.
But to apply this, we should know the exact form of ODE, so it's possible to become generalized.
Oh.
No, I don't think so
We only
because
say that here.
네, 데타를 알아야 돼.
아니
아.
세타는 ODE의
시계.
식에 있는 모든 함수를 그냥 나열해 놓은 매트릭스.
But actually, we can just call here is f of u, isn't it?
Yeah.
This is actually f of u.
저거 매트릭스 템으로 바꾼다고 저렇게 해놓은 거.
그냥 원래는 안 해도 돼요. So here we just have f of u, and we want to know f of u is monotonic or increasing or decreasing.
Oh,
Yeah, we need that, but we want to get that idea from this form. Please write down this. Yeah.
이거 다 말이 안 되는 것 같아.
It's not that difficult, I think. So we have a one Gobi team. Next Monday morning. Okay? And then who else? Wow. You can point out other person's project, that's also a good idea. But whereas we can use this integral by parts idea. Delay differential equation. Okay, COVID-19. Pitting.
But one concern is that for to calculate that all of the variable in U should be observable.
Yeah.
But for the CI, we only observe R. So maybe we need some modification.
Rather than every ODE variable, we only have a single ODE. So what Dongja's point is here, if it's a 4-variable differential equation, here we need an observation for all 4 variables. But in the typical case, we only observe the 1, 3 are hidden, like circadian clock, only protein, SEIR, we only observe the either R or I, something like that. In that case, can we use it? Because good thing of ODE is even we have only one single variable observation, we can still fit the model, right? What can we do here if we cannot observe every variable?
딜레이 인베딩.
Tokens? So in this form, every U should be known.
Yep, there's
Can we go trap that discrete form?
in this part we should know.
Let's go discrete form. Okay,
So
here
we
we
should
have
know U and phi.
So here we assume that this U, let's say lambda Volterra 2 variable, then x and y are all observable, right? And then here as well, right? What if we have only x is observed?
아, 근데 테스트 펑션은 그쪽 뒷면에만 주면 돼요.
저거를 계산하려면
다 있어야 되니까.
아, 그게 문제구나.
That's a very good idea. What if we have only here also we have unknown? Can we still serve? 지금 안 나. 그러니까 여기도 구멍이 있고 이 사각형 매트릭스에도 변수가 들어가 있는 거죠. 파라미터처럼. If we everything is observed, then known, known, unknown, completely separable. Unknown, some unknown. 그러네. 그렇구나. Yeah. But that's a good idea. If we don't have complete observation for every variable, what can we do? What if okay, what if this? Let's use that what the idea we learned. Say Fourier U is two variable system. Okay, but let's say only this is observable. This is hidden. That's the situation we are worried about it, right? But what I want to do is step 1. Let's make a fake U vector. How? This is observed. U2 here is random. Whatever, just plug in whatever data set. Just let's make a Hyun's daughter throw them. Right? It's fine. Now we have a U. Then can we solve this then?
Random.
Oh, anyway, these two
Yeah.
data are given. If we believe that's true, then we can solve it, right? Okay, let's solve it. Serve. The serve result will have some first parameter set. Correct? Because now we have a parameter set omega 1. That means we have
testing.
ODE 1. We have ODE and we have all the known parameter. Then can we solve this differential equation? Yes? Then let's solve this ODE equation. Let me call U2 vector is. U1 is always observed. Now, solution of this. Let's plug in here. And then repeat. What do you think? Work or not? My guess is if there is, it should work, isn't it? Yeah, of course from the random we will have a very wrong omega 1. But anyway, we have some omega 1 so that, or rather than random, maybe we can begin it whatever omega, then plug in that solution. And then let's update the new omega. Based on that new omega, let's solve the ODE. Only unknown part. This is always should be fixed. Then it should converge. What do you think? Can we do for COVID-19? Because if ODE fitting works, that means from the single variable observation anyway, the hidden observation also should fixed, right?
Yes.
That means this one should go some places. Okay. Hidden WENDy. COVID-19. 정표 it's you. So we have Hindi and what was that? With WENDy. With Kobe. Not Hongju, sorry. What else?